Hi, everyone. On behalf of the WM Keck Institute for Space Studies, I'd like to welcome you to today's event. My name's Michelle Judd, and I'm the Executive Director for the Institute. We will always be grateful for the special startup funding we received from the WM Keck Foundation, and as we continue to be privately funded as a think tank, we are very grateful to our current private donors and to the Caltech Space Innovation Council, without whom our current work would not be possible. So the Keck Institute for Space Studies, or KISS, is a joint think tank between Caltech and the Jet Propulsion Laboratory, JPL, and we're focused on ways to revolutionize space exploration. KISS is kind of like the Caltech campus. We are small but mighty. We are currently ranked as one of the top tier science and technology think tanks in the United States and internationally. So this lecture series is designed for the KISS affiliates. Affiliates are a small group of graduate students and postdocs who are nominated by faculty to interact with leaders in space exploration and learn about new missions like this particular one, Dragonfly. So what makes this lecture even more special is that we are holding it in concert with a virtual study we're currently running entitled Nebulae, Deep Space Computing Clouds. So to introduce our speaker today, I'd love for you to meet Mike O'Connell. Mike is a third-year graduate student in GALCET, which is the aerospace department here at Caltech. And he hopes that his research at Caltech will push the limits of autonomous robotics operations in space and in extreme environments. And during COVID-19, he can't really go do what he loves to do, which is mountain sports. So like any great Caltech student, he has put his energy elsewhere, and he's now brewing beer. So I'm sure it is delicious, and I can't wait to try it. And so Mike, you've been an affiliate since 2018, and you're currently our KISS affiliates liaison. So we could not be happier to have you, so take it away.
Hi everyone, thanks Michelle. And thank you everyone for tuning in for this exciting talk. Tonight we're going to hear about an incredible mission from a distinguished speaker, Dr. Douglas Adams. Dr. Adams currently serves as the lead spacecraft systems engineer for the Dragonfly mission at the Johns Hopkins Applied Physics Lab. Dr. Adams grew up in Ames, Iowa. Then he went to Purdue University, where he earned his bachelor's, master's, and doctoral degrees. After finishing his degrees, Dr. Adams worked quite close by to us here in Pasadena, where he worked at the Jet Propulsion Laboratory starting in 2001. He contributed to many missions, mostly working on structural mechanics, attitude dynamics and control, and systems engineering. In 2013, Dr. Adams moved to the Johns Hopkins University Applied Physics Laboratory. And as I mentioned earlier there, he's currently working on the Dragonfly, which will explore Saturn's largest moon, Titan. Throughout his career, Dr. Adams has distinguished himself with a number of awards, including the Astronaut Scholarship Foundation's Neil Armstrong Award of Excellence, the Applied Physics Lab Bumblebee Award, NASA's Exceptional Achievement Medal, and several other honors and achievements. Dr. Adams has published and contributed to the number I saw was 47 papers and presented at a number of conferences, but I'm sure that number is always growing. Dr. Adams is also an instrument-rated pilot. He's an Eagle Scout. He's well-traveled. He's been to 48 of the 50 states, still only needs to go to North Dakota and Alaska. And he would surprise any of us with his skills as an advanced hobbyist figure skater, where I'm told his favorite tricks mostly involve the jumps. So I hope everyone joining us today is as excited as I am for this talk. And I would like to extend a warm KISS welcome to Dr. Douglas Adams.
All right. Hey, everybody. I'm gonna share my screen here. So hopefully that's coming across good. All right, it's wonderful to get to talk to everyone, and I apologize that this is done remotely. It's always better to be there in person. I'm very excited to talk to you about our mission Dragonfly. And as Mike indicated, we are going to Saturn. I want to start just by pointing out a very interesting thing. This image on the right is not a construct. This is not a Photoshop special. This is a real image that was taken, and you can actually see the landing site that we're targeting in this image. So it's a marvelous picture, just a little bit of a tease for where we're going in the future. So Titan is a rather compelling place from a science perspective. As you are aware, one of the great programs in NASA is the Origins effort, looking for origins of life. And on Earth, life has overprinted our distant past, but there are places elsewhere in the solar system, and Titan is one of them, where early prebiotic chemistry still exists. And it turns out that when we go to Mars, for instance, we search for fractions of grams of carbon. On Titan, we actually have the opposite problem. Most of the surface is covered in carbon and carbon compounds. So it's a very exciting place. It is also an ocean world. There is a subsurface ocean that is on top of an ice core and a silicate rock core. So it's an exciting place to go for geology as well, planetary geology. In particular to our mission Dragonfly, Titan has some very endearing properties. Most especially the surface gravity you can see is only 14% of Earth's, and the atmospheric density is a little over almost 4.5 times Earth density. So that makes it an ideal place to fly, so much so that famously, if you were on Titan as an astronaut, two things. One is you could jump in the air and flap your arms and fly like a bird. The other thing is that if you fell out of an airplane, you would survive the fall. You could basically just land on your feet. The terminal velocity is that low. The penalty you pay for that, though, is the bitter cold. And you can see at the bottom, the temperature is only 94 Kelvin or minus 290 Fahrenheit. So it's a very cold place, but that's part of what contributes to the density. But it is a wonderful place to fly. Interestingly enough, again, and you saw this in the trivia, just before the presentation, it is the second largest moon in the solar system and the only moon with any kind of appreciable atmosphere. It actually has the second thickest atmosphere of any rocky body in the solar system behind Venus. Like Earth, it has seasons. In fact, its axial tilt is not that different from Earth. Earth's axial tilt is about 23.5 degrees, Saturn's 26.7. And so if you were to look at Saturn now, it would look something like you see on the right of the screen near the northern summer solstice. And in fact, it's quite beautiful. I encourage you to do that. I looked at Saturn just about a month ago. And the other thing that I'll note is at the bottom here, Titan's day, Titan is in tidal lock with Saturn, much like Earth's moon. So the same side of Titan faces Saturn the whole time. So its day it is the same as its orbit period, which is 16 Earth days long. We call that a T-sol, or a Titan solar day. So Titan has been explored. Well, it has been explored in the past. And this is just a very brief history of that exploration. The first spacecraft was Pioneer, and then both Voyagers flew by. But most recently, the Cassini mission flew to Titan and brought with it the Huygens probe. And this is what Titan looked like to us based on the Voyager 2 information. And at the time, when I was in college, this was the best picture we had available of the moon Titan. And what Cassini did for us is it unveiled Titan. And it did it two ways. The first way is this very large probe you see on the side of the spacecraft here. This is the Huygens probe that flew on the Cassini spacecraft, which you see this here. And you can get an idea for the size scale looking at the engineers over here next to the probe. And that combination of the probe and Cassini gave us a wonderful set of data about Titan. And we are capitalizing on that data in Dragonfly. So in particular, Cassini did 126 close flybys of Titan, and that data provided us with an exquisite look at the tantalizing look, I should say, at the surface of Titan. But Also famously, the Huygens probe made it to the surface and took the first ever picture of the surface of Titan, which you can see on the right here. And it's been put in the same perspective, or the perspective of a lunar image has been put next to it to give you an idea of the field of view that you're seeing. For reference, those little rocks in the foreground are cobbles. They're roughly the size of a large grapefruit, or maybe a little smaller than a volleyball or something like that. And they're ice, they're not rocks. Okay, but the other thing that Cassini did for us, in addition to ferrying Huygens there and collecting the wonderful data we got from Huygens on the surface, is that it took a great deal of imaging and radar information. And as you saw before, we were able, through multispectral processing, to unveil the surface of Titan. And what we found was this, and this is a Mercator projection of the surface. And you can see this brown region across the center of the map here. This is what we call the equatorial dune sea. And this actually, again, is the Selk crater, S-E-L-K, Selk crater. That's where we're going. And that equatorial dune sea is an ideal place to land. And we'll touch a little bit more on that in just a second. But that's one of the reasons that we picked the Selk crater, is that it provided a very special blend of an area that had access to these dunes, which are hydrocarbon sand dunes, that were blended with ice, melted liquid water ice that came out of this impact crater. So you had aqueous chemistry, aqueous carbon chemistry on the surface of Titan. And that's what we're flying there to investigate. It's going to be a fascinating mission. Again, though, in particular, and this is a bit busy here, but again, I'll just point out, here is the Selk crater. And what's not quite evident is there's a particularly good radar pass that goes right over the Selk crater and images below the Selk crater. And that is how we pick our landing site, as we go within that data. And one of the things the Cassini data shows us is that the equatorial dune sea is in fact just that. It's these large linear dunes, and you can see some in this image. And this is a radar image, so what you're seeing is the reflectivity of the radar, but the pattern is unmistakable. It looks very much like a fingerprint or something like that. And there are other features, other linear features you can see on the right over here. And we know these are dunes because there are dunes on Earth, in particular the Namib, which is a desert in Southwest Africa. You can look it up on Google Earth. Some very pretty pictures there. But we have synthetic aperture radar of Earth taken from orbit on Earth that looks exactly like this. So we know this is what we're going to expect on Titan. Fascinatingly, Titan also has other liquid features. There is a methane cycle on Titan. It rains methane there, and there are river channels, which are obvious. There are lakes in the northern hemisphere and southern hemisphere at the poles. And if you look very closely here, you can see a time-lapse image over here on the right. You can see clouds, methane clouds that are orbiting Titan, high-altitude clouds. So it's a wonderful place, a fascinating place, and a highly dense, scientifically rich target to explore. As I said earlier, one of the things that makes it interesting is the fact that it does have a liquid cycle. There is water, there's also methane, but it has the three key ingredients for life. There's an energy source, there is sunlight, it's very dim, but it's there. There is also potential chemical energy. There's clearly organic material, and as I just said, there are liquids. So prebiotic chemistry, we don't expect to find life, extant life on Titan now. It's just simply too cold. But the fact that there's chemistry there that could indicate the precursors to life in this environment is the reason that we're interested. And one of the other things about that is that one of the reasons that we have Dragonfly, this mobile explorer, this flight explorer, is to be able to investigate that environment. You need to be able to cover large distances over terrain that is not well understood. And in particular, the dunes can be highly inhospitable to a rover-style vehicle. If you think about the fact that you would have to crest every dune to get over it and then drive down the opposite side, the status of the dunes is unclear. We don't really have a lot of information. In fact, I didn't mention it, but on the radar image, the best data we have is about 300 meter pixels. So the best you can do is say roughly what 3 football fields would look like. And that's only range data. We don't have actual textural data. So we have to go there with a system that is robust to that environment and prepared to handle it, and then able to move within it in order to reach these science goals. So previous strategies to do that, there were a number of them that were proposed. Ralph Lorenz, who actually co-created the Dragonfly idea or concept, that he is our mission architect, but he had originally proposed a helicopter back in the year 2000. Other proposals for airships, Montgolfiers, airplanes. There was a proposal for the Titan Maria Explorer, which is time. And there have been NASA flagship and other studies to go to Saturn. But mobility has often been a key for these things. And again, powered flight on Titan is made easy by the high density and low gravity. So this is the solution that we came up with, and I'm here to introduce you to Dragonfly. So you can see the lander, what we call a rotorcraft lander on the right. And this is what it might look like when it's flying. And of course, the way we get it there is we have to house it in an aeroshell. We do a direct entry at Titan. We hit the atmosphere at about 7.3 kilometers a second, which is similar to Mars entries, order of Mach 25. But you'll notice that the spacecraft is round and highly axisymmetric. And the reason for that is, without going into great detail, the mission is powered by what's called a multi-mission radioisotope thermal electric generator, or an MMRTG, which is this round cylinder you see on the rear. It's contained within it. And that MMRTG does not put out a lot of electric power. It's order of what you might get out of a 75-watt light bulb at the end of the mission. More like 100 watts at the beginning. So in order to get from Earth to Titan, we have to spin the spacecraft so that it's spun like a gyroscope or like a frisbee, so that it's stable and we can maintain its orientation without having to consume power. And that way we can get to the surface. And then when we get to the surface, the way that we're able to fly is we sit on the surface and we trickle charge a very large battery, something like 300 pounds, a very, very large battery that's held within the warm interior of the lander. And we trickle charge that so that we store up enough energy that we can then move the rotors and affect the flight. I will note also that the RTG puts out about 2,000 watts of thermal energy, and we also convey that thermal energy into the body of the lander to keep the interior of the lander. So the interior of the lander is much like a cold day on Earth, like a crisp winter day, whereas, of course, outside it's a cryogenic temperature. So it's a very delicate balance of thermal engineering to make that work. Some other key features, I mentioned the MMRTG a minute ago, but also we're not fortunate enough, as we are here on Earth or even Mars, to have orbiting assets to relay communications. We have to use direct to Earth or D2E comm, and that's what this is a radial line slot array antenna, X-band array antenna that we use to transmit directly to Earth. If you're interested, about the best data rate we get is order of 2 kilobits per second, or roughly 2 Hayes modems, for those of you that remember what those were back in the day. But integrated over time, it adds up to a very wonderful science mission. And we also need to be able to do both aerial and surface imaging. And we have a requirement to be able to fly to altitude to get to be able to do atmospheric profiles as an experiment. Quickly, some of the instruments, and we'll talk a little bit more about one of them, the first one in particular, DRAMS, the Dragonfly mass spectrometer, which is accompanied by the Draco drill system. And again, I'll talk about that more in a second. We also carry a gamma ray and neutron spectrometer, which is in the belly of the lander and is used to measure the bulk surface composition underneath the lander. Interestingly enough, I'll just mention that we use a pulse neutron generator. You'll notice Schlumberger, anybody that's familiar with oil drilling equipment, Schlumberger is a major supplier of oil drilling equipment, and we in fact borrow the technology from oil wells to fly to Titan, which is a nice little synergy there. We also have a geophysics and meteorologic package. This includes, there are sensors, seismometer sensors on the skids. There are also atmospheric sensors. There's a hydrogen sensor on the side and wind sensors. And we also have a seismometer that we lower to the surface. That's the JAXA seismometer that's mentioned here. And of course, we are replete with cameras. We actually have 10 cameras on board. including the two PanCam cameras that you see up here, which are mounted to the high gain antenna, which allow us to generate panoramic images that can then be mosaicked to create a panorama. And very exciting science. So again, the reason we picked that, you remember I mentioned before that we want to go below Selk, and you can see this swath of particularly good Cassini radar information, and you can see the line between the other data that's not quite as high quality and this high quality data. So we're targeting our landing site in here because this is the place where we have the best information. And this is an image, an aerial image of the Namib that I mentioned before. You can see these large linear dunes, and they're order of 3 kilometer separation between them, 2 to 4 kilometer separation. But one of the features that we're most interested in is the interdune region, the area between, which is very flat, and you could see that you know, would be a golden place to put a lander, and that is in fact why we're targeting the dunes. So the plan is to not unlike what was done for Mars Science Laboratory Curiosity, is to land where we know it's safe and then drive to the science. We have the same basic approach that we're using here for Dragonfly. And this is just an image. We actually commissioned a satellite stereo pair image of the Namib, and we use that to help train the mobility system. And you'll again see some of that a little bit later. But this just shows you again these linear dunes, and you can see how Cassini-like it is, and how the interior of the dunes are what we would call obstacle-free. So one of the more intriguing things about sending something to Titan, which is in round numbers, it's about a little under 3 hours round trip light time to get to and from Titan. So it's not the kind of thing that you can joystick. You know, it takes, you have to send something that's autonomous. So we don't want to have the 7 minutes of terror where we have to, you know, trust this autonomous system to make a landing on its own every time. So what we did was we created this leapfrog strategy. Now, if you imagine, what you can do is that the first landing it has to be autonomous. We can't help it with that. So we have to teach it how to land the first time. But once you're on the surface, what you can do is you can take off from the green here, fly over, survey a site, and come back and land at the green. So you've primed the pump. So now what you have is you have data at both the green and the blue. And the next time you fly, what you can do is you can take off, overfly the blue, survey a new site, and then come back and land at the previously scouted site. So what this allows us to do is 2 steps forward, 1 step back, and we can basically dune hop, if you want to think of that. We can skip dunes, but every time we're landing at a site that has already been approved through a ground in the loop process, where we've downlinked data from Saturn, from Titan, and then gone through an engineering and science assessment of that, and then uploaded a target to the lander, which then autonomously navigates back to that. And we'll talk more about how we actually pull that off in just a second. A very quick look. This is a bit busy, but so I won't go into all the detail, but a very quick look. Again, remember that it's an 8-day day, so the sun is above the horizon for 8 Earth days. So 1.5 hours on Titan is 24 hours on Earth. So our plan is we would wake up in the morning, do a telecom pass with Earth, upload our flight plan, and then 24 hours later, the lander would execute it. If for some reason the lander waves off, either it's windy or Earth says, hey, we didn't really like what we sent you before, we changed our mind, then there's a backup opportunity at 10:30 local solar time. If you miss that, then we wait and we come around and we try it the next day. The reason we want to fly in the morning when the sun is that we want an oblique angle from the sun, roughly 45 to 60 degrees type of angle. And if you get more than that, if you get like direct overhead sun, then it doesn't illuminate the surface properly, so you can't navigate optically, and I'll show you the optical nav again in a second. Interestingly enough, when we land within 1 solar week of when Huygens landed, and at almost exactly the same time of day. We more or less split the difference, but in the afternoon instead of the morning. So we land in the afternoon and then we turn around and fly the next morning. And then of course, overnight we have a long period of time to come up with a new flight plan, and then we fly again. Our current plan is to fly once every 2 TSOLs, so every 32 days, which means that we're on the ground, and I get to use the word literally correctly. We are literally on the ground 99.9% of the time when we're on Titan. So we mostly do science and transmit to Earth with flying about once a month. I am not going to go through everything on this chart. I just know that there are people that are going to be interested in the processing that we do. Again, the main function is to be able to fly, navigate and fly between different targeted sites. And we have to do that in an environment that is very alien to Earth and quite frankly, alien to Mars too. And there are many different layers to the system. Very briefly, and again, I'm just going to hit a few highlights. There's a lidar terrain sensor. That's what LTS is. There's a radar and an environmental terrain sensor that we have here. So we use these things to process the surface observations that feed into a navigation filter. And we have a flight mode manager that's executing. This is basically where the pilot would sit. If you were sitting on board, you would be the flight mode manager. So you're telling the craft, the flight controller, what to do based on the navigation information. The only other thing I'll mention on this briefly, and then we'll move on, there's two. One is that our computer is a RAD 750, which at latest count, my memory is that was designed in 1998. So if you have an iPhone in your hand, you probably have at least, an order of magnitude more computing power than we have on this in this computer. So what we do is we add horsepower. There's a Vertex 5 FPGA, a field programmable gate array, that does the heavy lifting for the image processing so that we can get around on the surface. And I'll show you that in just a second. For the dynamicists in the crowd, of course, there's a dynamics model, both rigid body dynamics, flexible body dynamics, and aerodynamics. We treat the lander as rigid, but the rotors really are flexible, so we have to take that into account when we design the vehicle. And then when we're flying, the way we get around is we have a suite of cameras. In this case, I've also identified there's some micro imagers and downward looking science cameras that are in the belly here. But what we care about are the forward science cameras, nav cams, and the lidars, which are in the front. And there's another look at those here. You can kind of see how we've crammed all the navigation instruments in the front. There's a radar on the chin of the lander. There's redundant IMUs, redundant lidars, redundant nav cams. We also have a pressure sensor because we get pressure altitude. And much like flying a plane on Earth, pressure altitude is important to us. In fact, we use that as our averaging reference. And interestingly enough, we also make use of the atmosphere. We have an ultrasonic sensor that we use for fine altitude measurements as we approach a landing site so that we can control our vertical descent rate with precision. Again, I'm not going to go a whole lot into this. I just want to show a couple things. There is because I'm going to show you a movie on the next slide that explains this. But we take camera images and we do very much what the human eye would do is we compare two images to each other in order to be able to track our way across the ground. And you'll see these steps that executed in the movie, but you normalize it, warp it, you window it, and then you do a phase-only correlation between the images to determine a difference in position. And just real quick, this is what the windowing does for you. You have an unwindowed image, and you apply a hand window, and what that does is it smooths out the corners, and it gives you a much sharper correlation matrix. So you can see the kind of blurring and secondary features that you get here. But when you have that hand window in place, it gives you a very sharp peak, and that's very helpful. So before I hit go on this movie, a quick introduction to it. So what you're going to see is the incoming image in the upper left. This is the current image, and it's going to be compared either to the previous image, so it's an image-to-image comparison, or it's going to be compared to an image that was stored, and we call those breadcrumbs, like Hansel and Gretel. So when we've flown somewhere, and you can see the breadcrumbs, so in this case, we flew outbound on this green section, and now we're trying to fly back, and we're trying to track these green images. So you take an image, you resample it, you compare it to the reference image, you score it. If it passes the scoring, then it's admitted into the Kalman filter for navigation, and you move forward. So it looks something like this, and we compare images on 1 second centers. So every second, we take a panchromatic black and white image of the surface, and you can see how little information there really is. This is not unlike flying over a glacier on Earth or something. It's very flat, very smooth. So what makes for a very good landing site makes for rotten image correlations because you don't have much information to go off. So a human actually would have a difficult time correlating these images. But because we're doing it mathematically using the full frame image, we're able to do it very well, and you can see the correlation spikes down here. And what you see here is where our navigation filter thinks it is the blue, and the truth is actually the black. But the interesting thing is we don't care that the actual truth state is off, because that's admissible. We allow that. What we care is that we're able to fly to where the image is. And because our truth is what we see with the cameras, again, it's very much like you were riding on board. So being able to fly and recognize the breadcrumbs and retrace our steps allows us to go out and back and find where we took off from and land within meters of the objective target. We also have to, of course, be very careful with landing sites. Those that have worked Mars missions or any landed mission for that matter, you have to be very careful to avoid hazards and hazardous terrain. And what we've thus far identified is as hazardous terrain is anything that's larger than a 10-degree slope and or has a 1/4 meter rock. This is what we jokingly call this a NASA standard rock, hemispherical 1/2 meter diameter or 1/4 meter radius rock. So the way we do that is, remember I mentioned we have this lidar system. So as we're flying Dragonfly, you can imagine we're push brooming across with a lidar, and I'll hit go on this. So the truth is on the left, and you can see the image frames. We collect these at 10 hertz. And as we fly along, we're flying at 10 meters a second here. You can see the speckle in these images, but because we take so many of them, we're able to average that noise out and we get a measured elevation map. And from the measured elevation map, we're able to create deviations and slopes. And I'm gonna press play on that one more time. We're able to measure deviations and slope, and we can score those. And what you see on the right is a real-time assessment of what the best landing site is. So it thinks that's number 1, and then it just switched those over there. So now this is number 1, number 2, and number 3. And then if you watch it, and this is being scored in this particular case based on the distance, the radius of the circle to the nearest hazard. And you'll see now it said, oh, this is now the best landing site. So after having flown this distance of about 100 meters, it's identified a prime landing site. And this is what it found. You can see the footprint of the lander here. And this is a full-scale version of what the lander would look like. And this is a very happy place to land. Very low slopes, very few rocks. And thus, using the LiDAR, we are able to find our own landing site in what we call an unscouted landing situation, where we have to find a landing site without any a priori knowledge of the scene, for instance, such as you have to do on the very first landing, or in what we would describe as a contingency situation when we're on Titan. If something were to go wrong and we needed to set down for some reason, a parameter is out of specification or whatever, battery low voltage or something, then you would use the same technology to pick a landing site on the fly. Otherwise, we use the ground in the loop. So the last thing I'm going to show you is a movie that kind of takes you through the whole mission. And we start out with, of course, the thing that Dragonfly does that most missions before it haven't had to do, is to deal with aerodynamics. You can see this is a cruise flight scenario, CFD solution, computational fluid dynamics. And you can imagine there's a large number of degrees of freedom that are involved with this. We also have wind tunnel testing. And in this case, we did some atmospheric testing in a cold chamber facility at Penn State University. This is a dual rotor configuration. You can see we didn't have a Titan environment, but we sprayed it with liquid nitrogen to try to make it cold. But we also, importantly, want to be able to validate the capability in the field. And so we have this little test platform that has this drone box on the bottom of it that has an iMUNA processor. You see the snow down here. We got very excited about the fact that there was snow, and we ran out in the field to fly over the snow, and then realized the grass was sticking through it. But this vomit-inducing video that you can see here on the right is a flight where it was terrain relative navigation done without GPS or compass information, and we were able to fly around and come back and land. And we're building a much more detailed platform for that. Of course, we have to get to space. As I mentioned, this is a spacecraft. This bird had a bad morning. This happens to be the MSL launch. We are also launching on a 5-meter fairing. NASA has not picked the rocket yet, but it will be a 5-meter fairing. That's the one thing we know for sure. And much like Cassini did a Venus-Earth Jupiter gravity assist, we are doing a Venus-Earth gravity assist with a launch in 2026. And it looks something like this. The little white thing is Earth, or excuse me, is the spacecraft, and you can see Venus is the green. There's our first Earth flyby, Earth being the blue, and then we go outside the Mars orbit. We do one big loop, and we come back for our second Earth. You can see the little triangles are trajectory correction maneuvers that we use to target Earth. This is Jupiter's orbit. Jupiter is unfortunately out of position for us, so we can't use it. but we were still able to reach Titan, and it's a long way to Titan. It's way out there. I mentioned the very thick atmosphere, 1,270 kilometers, ridiculously thick, and about 7.3 kilometers per second. We deploy a drogue parachute at 135 kilometer altitude or thereabouts. Bear in mind that we usually use 125 kilometers for the thickness of the Mars atmosphere, so we deploy a parachute above the altitude of the Mars atmosphere, and then we fall for the better part of 2 hours until we deploy the main parachute at 4 kilometers. Then we drop the heat shield. Once we drop the heat shield, it exposes the rotors, so we're able to counterspin the rotors to arrest whatever residual spin rate there is, and then we release the lander at 1.2 kilometers altitude, to fly. And it's on its own. It's now under powered flight, and it's on the clock because we had to find a landing site within the battery charge that's left over from the entry and descent. So as we mentioned, we do the landing reconnaissance we just discussed. It principally involves lidar in order to find a suitable landing site. And then we touch down, we do a soft landing. And the unique thing about Dragonfly is we have to do this 40 times. So we actually have a pneumatic set of dampers in the legs. What's shown here are the drills. These are part of the Draco system, and this is the pneumatic tubes with the blowers to pull air through to collect samples. You'll see that in a second. This is the carousel for managing the samples and the avionics unit that drives the whole thing. This is we call this the Iron Bird. It's a life-sized version of the lander that allowed us to mount the drill system, the Draco system on it. Here you can see we're doing a sample drill. The drill bit is specially designed so that it won't clog, and we're able to change the valving of the system to route the sample from either drill through either blower and through the sample system, so that we're redundant. And this is the sampling system itself. You can see a suite of these little sampling cups. And what we do is, you'll see in a second, we capture, as the blower is running, we capture the sample in those little cups for processing. And it's very much like a vacuum cleaner. You see the arrow here. So these are the tailings that the drill is kicking up, and it pulls it through the system, captures it in these little cups. When the cup is full, then then the sampling is complete. And then before we move the sample, I'll mention real quick, it turns out that ice at these temperatures is rock hard, like concrete hard. So we did testing of ice at LN2 temperatures. So before we do anything else, this is running a drill backwards to clean the interface there, and we pull air through to just kind of clear the system from that sample before we move on. And then once the sample's been collected, you'll see in a moment, you'll see what I like to refer to as the Breaking Bad field of view, where you're riding along here. There it is. There's your Breaking Bad field of view riding along with the sample. And then the carousel puts the sample into the mass spectrometer. And there's a gas chromatograph mass spectrometer and a laser desorption mass spectrometer that we can test. And then we get to do it again. We take off and fly to the next landing site, wherever that may be, wherever we may roam. And that's it. That's my summary of the Dragonfly mission. And with that, I'll escape, and we can return you to the Zoom meeting.
Thanks, Doug. That was a really cool overview, and we have a ton of questions, so we'll get started here. So the first question is, since Dragonfly is designed for low gravity, how do you perform flight tests on Earth?
Yeah, it's a great question. In fact, actually, I spent a large part of the last few years figuring that out. So the short answer is first I'll make an analogy to the Mars Science Laboratory and the Sky Crane. We were not able to test that either, right? It was all model-based. There was at one time talk of trying to do a powered flight test bed for that, but it just proved to be impossible, and it was de-scoped. In a similar way, what we have to do is we have an aggressive set of wind tunnel tests where we're able to quantify the rotor and rotor performance and the drag on the body. As you saw, CFD, and we carry healthy margins, control margins in the copter itself. We do have an Earth test campaign. You saw the quadcopter that we fly. We have built actually an octocopter that's a half-scale octocopter we call an integrated test platform. That does not help you with the dynamics. It doesn't. The Earth dynamics, gravity, and density are just too wrong. But it does give us a platform on which we can validate all of the performance for navigation and the interaction of the sensors and the flight control. But the short answer, which I just gave you the long one, but the short one is that we have to do aggressive testing to get sufficient data so that the modeled performance is correct on Titan.
Yeah, great, thank you. So our next question is, did you have to engineer the sensors, like the ultrasonic sensor mentioned in the presentation, for the denser atmosphere on Titan? And what kind of considerations went into that?
Yeah, so so first the easy one, the pressure sensors, it turns out that there are absolute pressure sensors that are available, common off the shelf units that we just bought one, or we're gonna buy some. The ultrasonics detector, actually, ultrasonics work marvelously regardless of the temperature, at least for the sound waves. We are going through a qualification program right now. We have a Titan environmental chamber that we've procured that's due to arrive at APL this fall. And the plan is to put these sensors in that chamber to prove that they work under Titan conditions, because we can match the Titan atmospheric pressure and density and temperature. But we can't do it on a flight platform. That's the difference. So you have to do the same kind of thing. You do piecemeal qualification to verify the performance under as flight-like a condition as you can. Right now, we don't anticipate, certainly for the cameras, we don't anticipate any issues with the thick atmosphere. The lidar is the same, being an optical, well, a near infrared instrument. We don't anticipate a problem there. And of course, the MIMU, the inertial measurement unit, we're not worried about that one either. So I hope that answers the question.
Yeah, it does. I think pretty well. So the next question is, I think you touched on this in the presentation, but how does Dragonfly communicate back with Earth? So
I'll actually give you a couple answers to this. First, on the surface, you saw the high gain antenna. We have a 100-watt X-band transmitter that we use to send signals to Earth. And actually the data rate I quoted, the 2 kilobits per second, that's assuming a single 34-meter DSN aperture on Earth. If you have additional assets, if you gang two of them together, or if you use a 70-meter antenna, then you get a corresponding increase in the data rate that you can get back. One of the more challenging things that we have to do, and this is something that we're working on right now, is that we need to be able to transmit, let's say, a heartbeat signal or some sort of health and status. It's called a tone, a semaphore tone, to Earth during critical operations. And those include entry, descent, and landing. And also, as it turns out, any flight on the surface, because if that flight were to go poorly, it puts the mission at risk. It's considered a critical event. So it's challenging because the geometry changes and the vehicle attitude changes, and you have very weak signal coming from Saturn as far as 10 AU from Earth. So it's challenging to get that back. But the short answer, again, is X-band transmission, and it depends on which antenna and which mode we're in to get the signal back.
So our next question is about the autonomous flight operations. And it is, do local weather patterns affect autonomous flight, stability of the Dragonfly, especially if you had something like high-speed winds or a storm rolling through? Yeah,
so we have some thinkers in the audience here. That's a good question. Everybody wants to know about weather on Titan. As I showed you, there are clouds, and we do know that it rains on Titan. The good news is we're landing kind of in the late winter on Titan, at least in the northern hemisphere. And what that means is it's kind of the dry season. So interestingly enough, we don't expect it to rain while we're there. And part of our pre-flight checks, and this is good, it's fun to go through the logic on this. You have this lander that you managed to get to the surface of Titan. It's safe on the surface. It's collected science on the surface. And now you're ready to relocate. Well, what kind of information do you need to have in hand before you allow the thing to autonomously take off and go do something? Well, part of our assessment is an onboard weather assessment. We actually have wind sensors on board that we can use. And interestingly enough, if it actually were raining, even though we don't expect it to be, but if it were, the rain would hit the wind sensors and it would provide an obvious signal that we would know it's raining. But moreover, to the wind question, we'll be able to detect if there's any untoward winds. Interestingly enough, so I mentioned 94 Kelvin on the surface. As people will remember, methane is a very good greenhouse gas, and 5% of Titan's atmosphere is methane. So the surface is almost isothermal. There's something on the order of like 1 Kelvin in diurnal cycle, day-night. So it's almost a constant temperature all the time. And what that means is that there's very little convection in the atmosphere. So there's not a lot of wind on the surface. We do have wind models, and we do expect it to not be zero. We are designing to permit winds, but we will be able to measure if the winds are high, and we can abort a flight before we take off. And we expect the winds to be low also. But hope's not a strategy, so that's why we bring the wind sensors with us. And that way we can make a real-time, the lander itself can make a real-time assessment about whether it's able to fly or not. Now, the last thing I'll add is that the flights are relatively short. I didn't mention it, they last about 30 minutes. And we don't expect the weather to change significantly in a 30-minute time span. So if the weather is good at takeoff, it should be good for the flight. And that's just, that's one of those things you kind of have to take with exploring Titan.
Yeah, so essentially you guys are being conservative with weather and when you fly.
We're doing our best to do so, that's correct.
Yeah. So the next question is about, do you consider a hybrid lift generation with fixed wings on rotors for the Dragonfly? What are the reasons for having only rotors for lift generation in your architecture?
So it's an interesting question. I'll add that actually, I didn't mention it, but we get some buoyant force because the interior is much warmer than the exterior, so it's slightly buoyant, but not a lot. Fixed wings, so one of the reasons that we have fixed pitch rotors, single degree of freedom fixed pitch rotors is because, again, the cryogenic, very dusty environment, we don't want to have mechanisms that are complicated. I'll use the helicopter as an extreme example. It's got a swash plate and a collective and lots of mechanisms, lots of moving parts. It's one of the most complicated machines that flies on Earth. And if anything goes wrong with that, we can't fix it in situations. So we need something that won't have a failure mechanism to it, or it minimizes the failure mechanism. So if you had say a tilt rotor like a V-22 Osprey or something like that, that introduces a failure mechanism that would be very risky. Now you could, for instance, try to have, and you saw that there was actually a proposal for an airplane that would just stay airborne all the time at Titan. It can be done, but we don't need that type of flight range. We don't need to fly hundreds of kilometers. We need to fly tens or fives of kilometers. And it turns out that you can do that very effectively with the rotor. And the other thing is that wings are not helpful when you're landing. If you think about trying to land on the surface, if you have a very long, like nice high aspect ratio, think of a glider. Well, unless you have very tall landing gear or an extremely flat or prepared landing site, it's difficult to land on the surface with large fixed wings. And we are investigating putting lifting body features on the lander, but it's difficult because the lander has to do things like communicate to Earth with a, high gain antenna, and it has cameras, and it has, other things on the exterior science instruments that get in the way. So, but that's the answer, is that we did think about fixed wings, but the fact that we need the vertical takeoff and landing capability, and the need to do it many times, meant we needed a platform that was robust. So we gave up flight distance for robustness, if you want to think of it that way.
Thank you. So our next question is less on the engineering side. What planetary protection measures are being used to make sure Dragonfly doesn't contaminate Titan with life from Earth?
So that's either a Mars scientist or a Europa scientist that's asking that question.
Yeah, and they give one example here. Would using a radioisotope thermoelectric power contaminate the Titan environment?
Yeah, okay, so that's a good question. So as we speak now, in this conversation, Titan is classified as a 2-star, category 2 star. So Europa, for instance, is category 4. So you have to be extremely careful when you go to a place like Europa or Enceladus. But Titan is so cold that, again, we don't expect extant life there. So as things stand right now, we don't expect to have to do planetary bakeouts, for instance, because now we will, for contamination control reasons, among other things, be very careful not to, not going to put a bunch of handprints all over the lander, but we don't require any special measures to protect against planetary protection concerns, at least in the current understanding. And that is going to be vetted. There's a science process. Of course, there's a planetary protection office at headquarters, and there's an international community that's got a stake in this too. But as we understand it today, even landing an RTG on the surface is not a concern, because it would never be able to burn through that thick ice sheet on the surface. And even if it did, it's unlikely we would find anything there. So,
our next question is, if I had $1 billion to invest to build support for communication devices around other planets or moons in our solar system, first, will we benefit from it, and would it make sense? And should we build space stations around these planets to make it easier to communicate with these machines?
So by space station, I take it they mean something that's manned or personed. I will suggest that in my lifetime, it's probably not practical to expect to send people to Saturn. Although if you've watched the movie Gattaca, they did it there, but that's a movie. So, but in terms of, I mentioned before, I lamented that we don't have an orbiting asset. If this were a flagship mission, we would have 2 components going with us. We would have a lander, and we would have an aerocapture orbiter that we would be able to use as a relay satellite. And that would probably multiply by at least 10, maybe 100, the data volume that we get off the surface, because you'd be able to send something using very low power transmission from the surface to an orbiter that could then be dedicated to downlink data, ad nauseum. As again, we have an 8-day night where we're effectively out of communication with Earth right now. But if you had an orbiting asset, you actually could conduct science at night as well, while you're doing that. The thing you have to be careful of, but I will go back to, is that we do need the power to fly. So if you conduct science all the time, then you can't fly. So there is a trade. The best way to think of that is it's really an energy balance for the mission. Is, if you integrate over time the energy, integrate over time the power that the RTG is putting out, that gives you total energy, and you can expend that energy on what you choose. Either you do science, you transmit data, or you fly, and there's some balance to that. But we would love to have an orbiting asset at Titan. The issue about just putting one there and waiting for something to join you is that there are practical lives to space assets too. Earth satellites, they typically have a 15-year lifespan, for instance, the GeoBirds that are up. So if you have $1 billion handy and you're looking for something to spend it on, we'd love to have a ComSat. Please, 2026, you got plenty of time to design it. Be easy. So.
Yeah, I'll with my next $1 billion, I'll put it out there.
Yeah. That's what I'm going to do with my third $1 billion, I think. So.
So our next question is, how can you ensure hardware is robust to the molecular composition of the surface and atmosphere?
So we have a pretty good idea, again, back to so we know the atmosphere pretty well, right? We actually had Huygens that descended through the atmosphere. So we have direct measurements of the atmosphere. And we have a very good idea, and it's chemically inert, at least as far as we're concerned. There's 0 oxygen, and there's no water at all. There's 0 humidity, because at 94 Kelvin, the water is all frozen out on the surface. So you don't have to worry about anything corroding or rusting, if it happens to be a threat of rusting. We do pay attention to methane. That's one of the things we check to make sure that nothing we're sending up is, sensitive to methane. But otherwise, it's really hydrocarbons, and there isn't any aggressive chemistry. We're not aware of or don't expect any aggressive chemistry on the surface. That would be an engineering problem. again, there is the bit of staring at the sun in terms of, the mass spectrometry is a bit challenging because there's so much signal, but the instrument's being designed to accommodate that.
Thank you. So our last question, I know that we had a bunch, and unfortunately we couldn't get to all of them. So the last question is, what is the autonomy level of Dragonfly? I think, there's different operation phases, but can we just go over again, where is there human input to how it flies, and at what levels are people involved in operations?
Okay, good. Yeah, I didn't get into this, but I'll ask you to remember, if you can recall the leapfrog image, right? You had a takeoff, a climb, a cruise, a descent. What we do is we have a thing, I mentioned this, we have a flight mode manager, and the reason we called it that flight mode manager is we have a bunch of flight primitives. So you say, okay, well, if you have a mode that is takeoff, right, and there's a set of parameters that you can put in that describe what the takeoff is that you want it to do, how high you want it to go, and how fast you want it to happen, and so you can upload a table of parameters that fit into that takeoff mode, and then you tell the lander, after you've taken off and you've achieved the objective of that takeoff mode, then transition to the next mode, which would be cruise climb. So then it'll pitch forward and start climbing. And again, there's a set of parameters, it's kind of like, an air traffic controller, you're cleared to 4,000 feet or whatever. So it's gonna, it's gonna be told, okay, I want to fly forward at this glide slope or flight path angle, and I want to climb from where I am to this elevation, this pressure elevation, etc. So basically you have these different primitives for the different functions that you have to do in flight. And on Earth, our flight planning that we do during that long night cycle before we upload this parameter table is we simulate like crazy, and we come up with a set of parameters that we want it to execute that fit into these different modes. And so what we're actually transmitting is a series of instructions that say, okay, it's recipes basically, and we're just changing the recipe a little bit each time for where we say fly this altitude, this heading for this far. And one other thing that I'll add that's interesting is that because again, there's no GPS, there's no magnetic field, we don't have any maps of Titan. All we have is these orbit imagery. We actually do radio navigation, the same kind of navigation that we use to navigate in interplanetary space on the surface of Titan to figure out where we are on the surface of Titan. So we do Doppler ranging and Delta Dor to figure out which set of dunes we are between, and we correlate that to the Cassini data. Anyway, back to the flight. The human in the loop is we have the data sets that's been downloaded. There's a series of NavCam images and lidar information, and we pour over that on Earth. We say, yeah, that's it, that pixel, we want the lander to land right there. And then we construct a set of instructions that say, use these breadcrumbs and fly this heading for this far, overfly the landing site, go out scout, come back and land where we told you to. And that's what we upload to the lander. And it has to do it all itself. So the level of autonomy is 100%. There's, in terms of execution, there's a great part of ground in the loop for preparation and planning, but execution is 100% autonomy.
Yeah, great, thank you. So that's gonna wrap up the questions. I do want to point out, I don't know if you've had a chance to look at the chat stream at all coming through, but everyone loves your jacket.
Oh yeah,
it's great. Yeah, the Dragonflies are perfect for the mission.
Yeah, I was very excited when I found it. I won't deny that. It's a lot of fun.
So as a small thank you for spending the time to prepare this presentation and meet us on Zoom, we sent you a small gift. So we're hoping you can open that now for us and show everyone what you got.
Gift box. So we'll open it up over here and see what we got. Oh, look. You got me another box. A box within a box. All right. Hey, all right. This is wonderful. Terrific. They're little coasters. So you see, it's a coaster. You see that?
Oh, cool.
They got me a coaster. They got I'll go quickly through them. There's one image, there's another with the lander coming down on the parachute. There's flying off into the sunset, that one, and lander on the surface with a high gain deployed. So outstanding, thank you very much, that's wonderful. They'll find a place of high honor in my living room.
Yeah, thank you. We really appreciate you taking the time for us.
Absolutely, it's been a pleasure.
So thank you so much, Dr. Douglas Adams. Thank you all of our guests for joining. We were over 500 participants at one point. So just right before we go, I want to say we hope to see you all at our next KISS webinar, which will be on October 19th. That'll be with Caltech's Professor Greg Hallinan regarding the FarSide mission, FarSide, a probe class mission to place a radio telescope on the lunar far side. So thanks again, everyone, for joining. Thank you, Dr. Adams. We'll see you all next time.